Hello, so here we are looking at GCSE Physics for CCEA 2015, and this is Unit 2. Question 2. The diagram shows a girl standing in front of a vertical plane mirror. To see all of her face, she does not require a mirror the length of the one shown. So this is one of these things where you have to establish how much mirror she needs. Well, because light will obey the law of reflection, we should really find the midpoints between her eye and the top of her head and between her eye and her chin, because that's where light coming from those places will obey the law of reflection and head into her eye. So there's the top part. So if you imagine this other bit here is the normal from light coming from her chin, that's going to head up that way and reflect with the same angle. That's why you need to find the midpoint so that it'll be the same angle either side, obeying the law of reflection. So really she only needs a mirror between the two normals there, those two blue lines. So we can start to look at these wee sections and see what size they are. The top half is 10 and the bottom bit there is 12 centimeters. So we can split this even into sections, 2 5s in the top, 2 6s in the bottom. That means that they only really need the bit between the blue bits, which is a 6 plus a 5, which means that they only need 11 centimeters of mirror. Okay, so that is the bit that's actually going to be needed, the bit between those two blue normals. And so we just do a wee calculation in the next bit to show that what they need is that middle bit, which is going to be the 6 and the 5 added together. So you just, part of the marks are going to be for this diagram, and part of the marks are going to be for a little calculation. So we've got light obeying the law of reflection there at the top. We've got also light's going to be obeying that law of reflection at the bottom as well, making an even angle, and that's why we need to find the midpoints in both cases so that it will be an even angle, with the angle of incidence being equal to the angle of reflection. So light from the top of her head will hit the midpoint on the way to the eye. Light from the chin will hit the midpoint on the way to the eye. And what we do now is basically just add those two bits up to give us that middle bit of mirror, which would be enough to see all the way to the top of the person's head and all the way to their chin. So by looking at the diagram, we can tell that we're going to have to add the two middle bits together, the 5 and the 6. So the minimum length is going to be 5 plus 6, which is where we get our 11 centimeters from. And that's that. Part B then. Rainbows are a common sight when the sun shines following a rain shower. Water droplets in the atmosphere are responsible for the colours seen. At X, sunlight is separated into many colours. And the diagram shows only the red and violet. So you can see the light being separated here, and it comes out at the end showing only the red and the violet. So we're asked then in part 1, what is this effect? Well, that's dispersion. And state briefly why it happens. Well, this is all to do with light being a mixture, and each one is refracted by a different amount because they have different speeds in the liquid. Part 2 then, at Y no light emerges from the raindrop. State what this effect is called and briefly why it happens. So you can see at Y here we've got this light coming back, no light emerging, and that's called total internal reflection. So that's total internal reflection occurring there. So we need to explain the concept of total internal reflection. So firstly what it is, and secondly why it happens. So it's called total internal reflection, and it happens because the angle of incidence for the light trying to leave the water is greater than the critical angle. Part C. To measure the focal length of a converging lens, the students set up the apparatus shown below. And you can see we have a lamp house, and a lens, and a screen. The lamp house with mesh is used as the object. She placed the object 20 centimeters from the lens and moved the screen until it produced a sharp image on the screen. The distance between the lens and the screen is not the focal length. Explain why. Well, to get a focal length from this setup, you need the object to be much further away than the lens, so that's the problem. The lamp house mesh is too close, and the mesh object needs to be several meters away for the image distance to be roughly f. So this lamp house needs to be much further away for this to work. She placed the object at greater and greater distances from the lens, and the graph opposite shows her results. What value for the focal length of the lens does the graph suggest? Explain your answer. Well, remember we said that the object distance has to get greater for the image distance to become the focal length. Well, that's sort of what the graph's showing. Let's take a look. So here's a section of the graph. And as you can see, as this object distance increases, the image distance here is gradually flattening off. And so this is tending towards the focal length. So it's obviously some value just down in here. We've only got to 2 meters worth of object distance. That's still not very far. So this is going to continue to creep down. So it'll be somewhere in this zone. So I would say this is suggesting that this thing will eventually level off at about 10 centimeters. So that's what we should put in. So it's going to be 10 centimeters, and the explanation is that this is the image distance for a distant object, according to the graph anyway. And this will also be the focal length of the lens, because that's our distant object method. You focus light from a distant object, it will be focused at a distance f from the lens. And this is the diagram. Light from a distant object will be parallel, more or less. The rays will be more or less parallel, and they will focus into a position and a point that's exactly one focal length from the lens, because that's where the focal point is. It's one focal length from the lens. So this is the definition of how a converging lens behaves, that parallel light will focus to one point. And so that's how the distant object method works. So back to your graph now, and we have this image distance versus object distance plot, and we're now asked a few questions about the graph. So we're told this magnification equation, that the size of the image over the size of the object will be the same as the image distance over the object distance. So either of those ratios can be thought of as the magnification of a system. It says, using the graph, determine the position of the object when it is the same size as the image. Well, that would also be when the image and object distances were the same, because the top and bottom line would have to be the same. So we're looking for values here where the object distance and image distance would be the same. And you can see here at 20 on one axis, where I equals 20, O also equals 20 centimeters, so that would be the place where those two are the same, and therefore the ratio will be 1. So I equal to 20, O equal to 20 is what we're looking for there. And that corresponds to putting your object at 2f out from the lens. So 20 centimeters would be the right value for that. In part 4, for object distances greater than 20, what does the graph tell us about the size of the image compared to the size of the object? So we need to have a look again at the graph after 20 centimeters. And you can see all those image distances are smaller. And if the image distances are smaller than the object distances, then the image sizes would be smaller than the object sizes. Part D, a converging lens. So it's a converging lens is used to make an image that is magnified and real. Complete the ray diagram to show how this is achieved. The principal focus has been marked F and the object has been marked O. Now, when you use a converging lens to produce a magnified and real image, then there's certain things that are going to be true. So we start by drawing a ray that's running parallel to the axis of the lens, and we know from our rules for rays that this will turn after going through the converging lens and head down through the focal point F. So we try and draw that. I'm just trying to draw that with the tools available to me here on the iPad. So a parallel light then turns and goes down through F. And then we have another ray that goes through the optical center, and it will pass straight through the lens undeviated as it goes through the optical center. And then where these two cross is the top of the image arrow. So the base of the image arrow will be on the axis. These represent the top of the image arrow. And so the image arrow will appear with its top just where those two rays are crossing. So in a ray diagram like this, it's important to show the direction of light travel on all your rays. So they're coming from the object and heading towards the image. So we put our arrows on. Apart from being real and magnified, what else describes the image? The position of the image is not what is required. Okay, so this is an inverted image. It's upside down compared to the original object. So that's what we want to say, that it's an inverted image. State one application of the lens used in this way. Well, we've made something bigger, so something like a photographic enlarger or possibly a projector would be an example of doing this, where we make a bigger copy, which is also real, so it will project onto a screen. So the photographic enlarger would be an example, but the most obvious one would be something like the projector. So we're making a big version of something that was smaller, and that's what happens when you project onto a big screen. And that, as they say, is that.